Let's see. I don't see the live stream here. It's live, okay. Oh, I can see it. Okay. Okay, I guess we're live right now. Finally. Yeah, sorry about that delay. We still didn't perfectly solve the problem, but we solved the problem good enough that we can proceed, I think. And thank you for suggesting sharing that screen. What's going on right now? Okay. Everybody's seeing the right thing, right? Okay, good. Well, welcome to the seminar. How many people already took digital design and computer architecture? Okay. How many people took computer architecture? Okay. How many people never took a course from me? Okay. Okay, so we have a variety of people. I guess people on Zoom can answer also, but I don't know if you saw any of the answers. Okay. That's a tough one. That's a difficulty with the hybrid mode now. Okay, as I expected, I mean, people who come to this class are from varied backgrounds. So I'll still give the introduction of logistics. Some of this may be a repeat of what you may have seen in digital design and computer architecture. No one here took a project and seminar class? Okay. Okay, since I think we've covered the entire set of classes. So welcome. For those of you who've taken a class, how do we reduce this? Okay, that's better. Now that I can see better. For those
Onur, could you wear the mic?
Say it again?
Could you wear the microphone? We're hearing you not well on Zoom.
I am actually wearing the microphone.
Okay, then it's on the computer mic currently, I think.
Okay, yeah, select the microphone. You can see that it doesn't give me an option of this Extron HDMI, which is your speaker right now. Any thoughts?
Yeah.
I don't know. Why don't you check? I didn't do that. Mohammed did it, but he's not here, I think. We can also increase the microphone level. Can you hear better now? For you guys, probably yes, but how about the Zoom people? Yeah. So how do you connect that? Okay. Yeah, you can see one of the challenges in computer architecture and system design today. Like having better seamless systems. Somehow I'm not very good at these seamless systems that just work right. Okay, yeah. How about that right now? Zoom people?
Yeah, if you walk away and we still hear you as well, then it's good.
Right now it says USB, Hersal, CHNC 14. Can you speak again?
Yeah, I think it's good, but it was good before
Much
also
better.
when you were in front of the laptop. So.
Can someone speak on Zoom? I guess they're speaking and we're not hearing. That's what I assume right now. Let's go back to Extron. How about right now?
Test,
can hear you.
3.
Then we have to do Extron. Okay, I'm not going to touch this at this point. This is, you don't understand the system and it works. Don't touch it. But at some point you need to rethink it, I think, which I think someone needs to do. Yeah, since you guys are younger, probably you will do a better job than our generation has done. Okay, this is also working, so I'm not going to touch this one either. Okay, welcome. A late welcome again. I think we're 15 minutes late. But let's start, I think. I hope this is working and it's working. Okay, for those of you who have not seen me, I'll introduce myself. I'm a professor here at ETH, been about 6 years. Before that, I was a professor at Carnegie University. I think what I'm going to do is, but I cannot do mute. Okay, maybe too loud, you're right. Because I increased this. Okay, right now it should be good, hopefully. Yeah, before that I was a professor at Carnegie Mellon University for some time. And before that, I started the computer architecture research group at Microsoft Research. and I was there for 2.5 years doing exciting research before I moved to academia. And again, during my career, I worked at many places, including Microsoft, clearly, but Google, VMware, Intel, AMD, a lot of interesting things for sure. I got my PhD from computer engineering from Texas, University of Texas at Austin in 2006. And since some of you have taken my courses, you probably have seen my PhD thesis also, which I'm still excited about. And if you want to do research, I recommend do something that you would be excited about in 20 years later also. Of course, you cannot fully predict that, right? I guess if you work on something really fundamental, yeah, but I mean, it depends on what kind of a person you are also, right? You may be excited about a lot of things that you get your hands into. And before that, I was a bachelor student. How many people are bachelor students? Okay, that's a good fraction. How many people are master students? Okay, that's usually a similar distribution where you get. How about other people? Are they PhD students? Do we have PhD students in class? Anybody else in any other status? Okay. Okay, that's good. We have a good distribution then. That's usually what happens. We get bachelor's and master students. And I was a bachelor student at the University of Michigan doing computer engineering and psychology long time ago. And again, you can reach me with email. My email tends to be a little bit unreliable because I get too much of it. So please resend. I think some of you already experienced that. Yeah, sorry about that. That doesn't mean I'm ignoring you. I just, especially these 2 years have been a bit crazy with the COVID. It's hard to catch up on email really. It's amazing, and with COVID expectations also rose. It's a bit weird. I mean, I can give you the story, right? We used to have these conferences. Normally you're invited to give a talk at a conference, right? That sounds nice. You travel, give the talk, you make the talk ready last minute on the plane or in your hotel room the previous night. That's what I do. Optimize it. And then you deliver the talk online. Everything is good. No problem. With COVID, online conferences, everything should be easier, right? Because you don't need to travel. Oh no, it's not easier. What happens is people ask for your talk 1 month before. So you got to finish your talk 1 month before the conference. Just in case you cannot deliver the talk online for whatever reason, like the connection reasons that we saw here, right? So you got to prepare the talk, record it, give it to them 1 month before, plus be ready to present online. That doesn't sound good, right? So I think this is the sort of thing that's kind of become a bit unreasonable, let's say, in the last 2 years. I don't understand. People are somehow not quite good at understanding the implications of this sort of thing, perhaps, on other people. But yeah, this is a kind of a first world problem, maybe. If this were the only problem in your life, that's good, I think. Yeah. Okay, anyway. This is something also maybe people need to think about, right? When we're dealing with both online and offline hybrid methods of teaching. How should things work? Like we had 15 minutes over here kind of wasted trying to make it work, but maybe there's a better system to be built for this sort of interaction. And we're trying to make virtual reality happen, right? I don't know. How many people have tried those virtual reality systems or mixed reality? Are they good? Kind of? On your eyes, interesting. Why? Okay, interesting. Anybody else who's had a similar experience or better experience? I don't know. Similar? I see. So we're not there yet, apparently. How long do these things last in terms of battery? Oh, okay. Yeah, if it's connected, then yeah, you're all powered. They last pretty long, really? Like 1 day? I see. Okay. Okay, that's not bad. That may be better than my computer, actually. Yeah. Okay, that's good. Maybe I should try these things one day. Okay. Anyway, okay. I think I've already talked about myself. Let's talk about research a little bit. I'll just give a brief introduction to what I do, what my philosophy is, and what the research group does, because you will actually interact with a lot of people in my research group. They're going to be your mentors when you present papers. And then we'll cover some course logistics. And then I think we'll be done after that today. Hopefully we'll be done early today. But whenever I say that, it goes long. So I'm going to shut my mouth right now. So I do research in computer architecture, systems, hardware security, bioinformatics, a lot of interesting topics to me. And you can see some topics over here. And we're going to actually choose papers related to these topics as well. Some of them will be very old papers. Some of them, well, we'll give you a choice of papers to choose from. And in the end, we will decide based on what you select as your top priorities. But we're going to cover topics that are spanning these areas and maybe more. But I think architecture is quite exciting today. And hopefully you're here because of that as well. Okay, maybe we'll cover some of these. So what we're doing in our research right now is building fundamentally better architectures. That's our goal, at least. How do we rethink the entire system, computing platform we design for a given workload or for general workloads? And how do you make it fundamentally better in different aspects, like energy efficiency, I think is critical, performance, security, safety, reliability, and also specializing the architecture for particular workloads. I think there's a lot of opportunity in these virtual reality systems, for example, to do better, in my opinion. I haven't studied them, so I'm just thinking that way right now. So these are not necessarily the only directions we follow, but some major directions that we look at in my group. And my group is relatively large, so this also is kind of representative of what's also happening in architecture, in my opinion. We'd like to design fundamentally secure, reliable, safe architectures, even though these three are different concepts. They're all important, and at some point they come together as well. Private, you can also add the privacy aspect over there too. How do you make systems fundamentally energy efficient, memory-centric, or data-centric? How do you make systems low latency and predictable? And then how do you design systems for key applications going into the future, especially those that will become even more important? This is more specialized architectures potentially, right? Machine learning, genomics, medicine, health. The usual way we look at architecture, especially those who have taken my courses would be familiar with this diagram, right? This is the transformation hierarchy. You have problems at the top of the computing stack, and you have electrons at the bottom of the computing stack. And your goal is to solve problems in computing, right? And this is the stack that we use today to express the problems in terms of electron language. And computer architecture traditionally deals with software hardware interface and microarchitecture. In fact, if you were taking like my courses in most of the other universities in the world, you would be dealing only with that part. You wouldn't be dealing with maybe the upper parts as much, but or research as well, right? But today, I think the expanded view of computer architecture is increasing. People are thinking across the stack, because in the end, the goal is to design much better computing platforms. And that spans not just the software hardware interface and the microarchitecture, but also spans the software that is on top of it, right? The algorithms that you design. And also it goes down to logic and devices, because there are some very interesting emerging technologies and devices that are down here, which we have mentioned in some of those courses, and especially went into detail with the computer architecture course, for example. We talked about emerging memory technologies and processing in memory devices, for example. We may cover some of those in this course also, actually, depending on the selection of the papers. But one example here today is machine learning accelerators. Like a lot of companies are designing machine learning accelerators today because we have a lot of data that goes into these training as well as inference in machine learning models. And to be able to keep up with that data and the computation that's required to operate on all of that data, we need specialized accelerators. General purpose computers do not work very well today. CPUs certainly do not scale very well. GPUs, even GPUs, very powerful computational engines, is not enough to do training of the biggest models today. So people are specializing and specializing. We have a lot of machine learning accelerators. And again, if you've taken the courses, we've discussed that. Maybe we'll discuss it next week. I'm not sure yet, but that's the idea. If you really want to achieve the highest energy efficiency and performance, you should really take this expanded view of computer architecture. Because if you're just dealing with software hardware interface and microarchitecture, you're losing possibilities of improvement on the higher level as well as lower levels of the stack. You're not customizing your algorithm to the underlying hardware as well. And we will see some papers, I think, in this course. Hopefully some of you will select them, that discusses this algorithm hardware co-design. How do you do that? What kind of benefits you get? I've given you some examples in past classes also. But this is what's happening a lot today, and this is what we're doing in our research, in part of our research, co-designing across the hierarchy algorithms to devices and specializing as much as possible within the design goals. Does this make sense to everyone? Okay, so for some of you, it's much more familiar, of course, right? You've seen the exact slide multiple times. Sorry about that. I like it. I like the slide. Okay, so this is a very busy slide of what we're doing in my group. Again, this doesn't cover everything, but I think it covers a lot of things. Like we have broad research spanning applications, systems, logic with architecture at the center. Processing in memory is a very interesting direction that's happening today. I don't know if I have slides for this. I don't think I do. But for example, this week, SK Hynix, which is the second major DRAM manufacturer, at the ISSCC conference is announcing their processing in memory engine also. They call it Accelerator in memory. It's based on graphics memory. And their goal is, again, accelerate machine learning workloads. Very similar to Samsung, what Samsung introduced last year. So major manufacturers are moving to putting computation capabilities inside the memory chips today, which is very exciting in my opinion. So now you got the cutting edge also this week. So there's a lot that's going on in architecture today. I think this processing in memory is very exciting. Certainly non-volatile memories are interesting. I think we've already kind of talked about this. I think we talked about it also. Some of you may be familiar with RowHammer, for example. You may read some papers related to hardware security, RowHammer and other types of hardware security issues. That tends to be popular papers that are selected and presented in this seminar. And architecture is specialized for machine learning, genomics, graph processing, medical applications. I think these are also quite interesting. Actually, there are a lot of papers that are written in this area today, like machine learning accelerators. If you go to a major architecture conference, a lot of papers are on that topic. Not necessarily very big advances. They're usually tweaking this part or this part of the system. But since the topic is deemed important in general, you would see a lot of papers. So it's hard to sift through all of those papers today. I'll suggest some papers perhaps, but I'll try to keep it to the really fundamental ones, let's say, as opposed to maybe not so fundamental ones. Okay, I'll not talk more about this. Let me introduce the group because you will see a lot of these people. Well, some of them have graduated, but you'll see some of them still. These are folks who are in my group. This is before the pandemic. This is, I guess, in the middle of the pandemic. And this is kind of, I'm not calling the end of the pandemic yet. I think science is not there yet. But this is, let's say, December 2021, where we finally got to get together in person. You can read the newsletters and see what kind of research they're doing. And these are the PhD and postdoc alumni, some of which you may have met who are not here anymore. Okay, if you're interested, you can learn more about the group. I'm not going to give you a picture of the group, but this video that we had given, I think it's only a 14-minute video that talks about Safari. Okay, so just to give you an overview of where this course stands, clearly some of you have taken digital design and computer architecture, and that's the basic course. And then we have an advanced computer architecture course. Some of you, fewer of you have taken, let's say. That's the more detailed research course that goes into a lot more issues in computer architecture. And this is where you are. You can actually find examples of past discussions, presentations in this course online. I don't know, have people seen it? Okay, you can find them online. Just if you want to get an idea of what's going to happen in a seminar session, for example, how did people present? How did the discussion go? You can find many examples online. We live stream some of them. This is based on your consent, of course. If the presenter consents to live streaming their lecture, we'll live stream them on YouTube. Right now, this is being live streamed, for example, assuming it's still working. It looks like it's still working. That's good. I saw 12 people watching online. But we live stream them, and I think you can. I'll show you some good well, I shouldn't say good example. I'll show you some examples that I think are good to follow. Let's say in the
in the later slides. Okay, so some of you have taken digital design and computer architecture. I'm teaching that also. In fact, we came directly from digital design and computer architecture to here. Usually Thursdays are a bit hectic because of that. Computer architecture, some of you have taken, seminar. This is the project courses which none of you have taken. If you're interested, you can also take these project courses, especially you must have an interest here since you're here. That's why I'm mentioning these courses. For example, we have a specialized course on processing in memory, another course on genomics, genomics acceleration, and you can see what we have covered, what kind of projects have been done. In general, we don't talk about the projects that have been done because they usually tend to be researchy projects and they're not ready to be exposed yet, at least to the public. And we have a heterogeneous systems course where we talk about, for example, GPUs, parallelism, and FPGAs. Actually, I have slides for only these three, but we have other ones like memory simulation, hands-on memory experiments, and also solid-state drives. And we have a new one on hardware software co-design, actually. These are hands-on project courses where a few students take. So you get to do some research projects in a semester that's hopefully interesting to you. I would suggest considering it if you have time in your schedule. We have a lot of live seminars. I think these are synergistic activities with this seminar, I think. We've started this last year also. We invite people. Some of them are from our group, some of them are outside. They talk about different things. You can see a lot of interesting topics going on: power management, security, processing in memory, memory scaling, machine learning. So there's a lot. But one of the main reasons why I'm showing you this is an opportunity, I think, to learn about cutting edge. For example, I think one of the recent seminars, February 2nd, was on UpMem's processing in memory engine. Fabrice Devaux, who is the chief architect of that machine, described that engine. And coming up next Monday, which I would recommend people to attend actually, the chief architect and co-founder of the Cerebras systems. Do people remember Cerebras systems? How many people? If you've taken DDC and if you have good memory, you may remember the wafer scale chip, right? These folks are the first people who have designed a real wafer scale chip. I think, I don't know how many trillions of transistors, basically, 60 times the size of a GPU. And their goal was to accelerate machine learning. And their goal was actually really because machine learning models require a lot of computation and memory at the same time, they were able to put both in a huge chip at the same time. So they have 40 gigabytes of one chip memory in that chip. 40 gigabytes is a lot, right? My computer has 8 gigabytes of off-chip memory, DRAM. They have 40 gigabytes of one-chip memory, SRAM, which is much faster memory also than DRAM, clearly. So their goal was to put a lot of computation, a lot of memory, and put them close. That's why they went wafer scale. And Sean, who's the chief architect, is going to talk about the entire system, not just the chip. He's going to talk about the chip, but he's also going to talk about how they built the entire system, cooling, how they scale up to a full data center. Because yes, this is a very powerful chip, but today's machine learning models require not just one of those chips, but thousands of those chips again. Yes. Yeah, that's a good question. I think I've heard numbers like, of course, they don't talk about their numbers. If you really want to buy them, you need to engage with them. Like big national laboratories and some supercomputing centers have bought them, or at least engaging with them. But I think I've heard numbers like over millions of dollars for the system, maybe $2+ million. For $2 million without. Yeah, renting could be cheaper. That's my guess. But I wouldn't rent something for $2 million unless you really, really need it then. Yeah. Maybe you can correct me and do some research. Okay. Yeah, I think this will be an exciting seminar. If you're interested, I recommend it. We'll share the Zoom link for people who are here. You don't have to attend on YouTube. You can if you want. It's your choice, but it's going to be open to public also. And Sean is a person who gives very nice talks. It will be full of insight, in my opinion. Okay, so I'd recommend everyone to attend. It's Monday, I think February 28th, Monday at 6 p.m. Any questions? Unfortunately, I don't have a picture of the chip. And I don't want to mess with my, actually, I will find it. Sorry, can you see it still? No, wow, amazing. Those guys also cannot see it. I guess it's not bad. So let me find a picture of this chip. It's not going to be hard because I used it in the previous class. Okay. Okay. Can you see it now? Okay, this is their first version, 2019. You can see this is a GPU, and compared to a GPU, they're a bit larger. And this is their second version in 2021, so it's even larger. So that's the 2.6 trillion transistors. And clearly there are a lot of issues when designing something like this, right? You can, yes, computational power memory, and they're close to each other. It's a lot. I mean, they have some other numbers you can find, and he will talk about in the seminar. But there are a lot of issues like how do you power up this thing? Because power consumption is a big issue for a chip like this. Reliability is a big issue if you have faults. How do you actually route around those faults? So they have an interconnect that enables them to route around the faults. So he will talk about the architectural design decisions they made, and he'll also talk about the entire system. How do you connect it? How do you cool it? And how do you map software to it? How do you map software to it is actually important because it's a different model. And they have compilers to take advantage of that model. Okay. Okay, it's essentially a SIMD process, single instruction multiple data process, many of them, as we have discussed in digital design and computer architecture briefly, right? Okay. No questions? Okay, I find this fascinating, and this is one of the examples where something really, really interesting is happening in architecture. Of course, cost may not be very favorable to this sort of thing at this point, right? Maybe in 20 years down the road, everybody will be building wafer scale chips, who knows? I don't know. I'm not sure. But chips in general are getting larger, actually. If you look at Apple M1, it's a large chip, SoC, system on a chip. It consists of CPUs, GPUs. Okay, I guess I'll switch. I think pictorial view is always better. Since I presented that also earlier, why not? I already have slides. Yeah, you've also seen this in some of the lectures, but you can see that this is, again, I think, even though it's a general purpose chip, it has a lot of special purpose components. Like the GPU is relatively special purpose. They have different cores, high performance cores and energy efficiency cores. And you can see that they're specialized also for different metrics, let's say. And then there's a neural engine, which is a machine learning accelerator. There's a vision engine somewhere that's not marked here. And there are other accelerators, perhaps, that's not marked over here, right? And you can see that there are system level caches. So systems are becoming quite interesting and complicated today. And a lot of the ideas that were in research have gone into systems like this. For example, heterogeneous multi-core processors were an idea that was originally published in 2001 or so, right? Well, 2003 or so, basically. In fact, it got the Test of Time award this year, well, last year in 2021, because it's affected a lot of systems like this. So this is a heterogeneous core microarchitecture, as you can see. So we will study some research papers that may have impact into the future also. And this is the max system. As you can see, it's much, let's say, larger. And if you want to put them into scale, chips are getting larger, right? Because you need to do more with these systems. Okay, maybe I'll go through some of these slides just to discuss, because I think I like this. If you have any questions, feel free to ask. At some point, we'll go into course logistics. But this is another chip, Tesla. You may have seen this again in my lectures, but more recently, you may have seen this chip also. This is a Dojo chip. So this was used for machine learning inference in their systems. This is designed for training, basically. It has actually some similarity to Cerebras, but it's a smaller, much smaller chip, as you can see, 50 billion transistors. But they designed the entire system to take advantage of the huge amount of data that they receive from self-driving cars all over the world, and then train a model that is better. Hopefully its accuracy and decision-making will be better with better training. So they actually burn a lot of power to build a better model. And this is a picture of their, like, let's say, cluster. You can think of this as a supercomputer, right? A supercomputer designed for machine learning training for the specialized purpose of Tesla's systems, which I think is fascinating to look into, right? People are companies are designing supercomputers like this for an important purpose, right? Okay, and I like this picture. This is from their AI day that they had, I think in 2021. I like this picture because it kind of resembles my picture earlier. It's not just about the chip, or it's not just about the software, it's all about the system stack basically, right? How do you build that system stack? And they build a system stack on top of it. They start with the chip, of course, with some architecture design, and then they build the system, and they build the compute cluster, and they build the software, and software is actually multiple things at the higher level so that they can take advantage of the chip. Okay, I just want to give you some examples of what's happening in computer architecture today. You still cannot see, huh? Okay. Maybe I'll mention, I mean, in this course, we'll take a broad overview of computer architecture. There are other things that are happening, like we have systems for genome sequence analysis. Maybe I'll mention that. Basically, the workloads are becoming a lot more demanding, right? You probably have seen this picture, but it's relatively old also, but people are designing genome sequencing devices. And now people are designing specialized systems that take advantage of the capability of these devices so that you can do processing much faster and much more efficiently. Answer questions like a virus detection, for example. How can you quickly detect a variant of a virus using data that's coming out of devices like this, genomic data? And usually, and you may have seen this, how many people took the digital design and computer architecture in 2020? Okay, some people over there. So you were folks, not 2020, 2021? Okay, you took all last year, which was fully online. Oh, okay, fully online is terrible, I think. What did you think? It was okay? Okay, some people say no, some people say okay. Yeah, it's a mixed reaction actually. Some people don't like it, some people really like fully online. I think with hybrid, you give the option to everyone, right? Everyone can get the best of both worlds, hopefully. But when I taught this in 2020, this was one of the last lectures we had in person. Actually, this was not the last, but I think this may be in the first lecture, actually. In the first lecture, I mentioned that beware of coronavirus, and this is what's happening. People are actually trying to understand what this virus is about and sequence it. You can see the date over there, 31st January 2020. But these devices, these fast sequencing devices that can do things reasonably accurate, they're actually quite important, I think, for us going into the future, for understanding of the diseases, understanding of the stuff that's going on, for public health in general, basically. So these folks, for example, did a study in New York City where they actually collected samples from the metro stations everywhere, or metro, and tried to have a map profile of the microbiomes that are in the city. So if you can do this at scale, you can understand what diseases may be lurking, right, going into the future. So this sort of thing could be very useful for outbreak prevention in the future, for example, right? Or I don't know, some good some analysis for public health. And some older devices were used for Ebola, and I think COVID-19. So we will have these outbreaks more and more into the future, in my opinion. We should be better prepared for it with computing system design. And I find this fascinating because people are building small machines, big machines, expensive machines, cheap machines. They all have different properties. And some of them are as small as this, as you can see. Okay, but in the end, I think we're bottlenecked by how fast and quickly, how efficiently we can process the data. Okay, now let me say one more thing in the slide deck, and then I'll go back to the other slide deck. If you have any questions, feel free to ask, by the way. We may cover some of the papers related to genomics and in general, computers for health and medicine acceleration. There are not that many papers on this topic, unfortunately, but it's becoming more and more. When we started the research, this was around 2007. We were one of the very few people looking into this, and then other people started looking into it. Right now, there's a good, let's say, healthy community that's looking into genomics acceleration, hardware, software, system design for genomics, for example. It's always good to have a healthy community. Okay, I'm looking for one more thing that I think is interesting. Yeah, this is one thing that you may see in Sean's talk. This is actually from another talk that he gave, but This is something to also think about. We may actually cover some machine learning accelerators, but this is an example of a very demanding workload, right? Neural networks are growing. As a result, both inference and training of neural networks is taking a lot of energy. I think here they're looking at training, for example, how much effort you need to take to train a model. And GPT-3 is one of the state-of-the-art, well, state-of-the-art in 2019 or so, models for language, like human-like language, if you will. And you can see that they have a lot of parameters, 175 billion. Soon we'll have 1 trillion parameters. Well, maybe it's already there actually. And we'll have multi-trillion parameters. And then of course, clearly the machines that need to train these models need to be very computationally as well as memory intensive. And this is, you can see that there's a data point over here. In just 2 years, you require more than 1800x computation. So this is exponentially growing. That's one of the reasons why people are building these machines for both training and inference. This example is training, but you can actually look at something similar for inference. Now there are 2 questions over here: how to design systems that are efficient, and then I think maybe the critical question is, are we really doing the right thing? I'm not sure, frankly. I'm not sure if these bigger and bigger models, because if you look at the data, the bigger and bigger models are providing less and less benefit as they become bigger and bigger. Because fundamentally, you're not changing the learning model. You're just adding more data and data to the process. And it's not clear if this is a really energy efficient way of doing things. People will still push the boundaries, of course, but I think we'll have more and more problems into the future in terms of the energy efficiency and sustainability of our systems if we actually keep investing with the same algorithms. That's why algorithm architecture co-design is important, but looking into new algorithms are also important, in my opinion. I mean, some of you may be studying machine learning. It probably is a good idea to look at much more efficient algorithms to do the learning. Any questions or thoughts? I find this fascinating because somehow neural networks have been important, no question about that, but they're a bit hyped to do a lot of things. It feels like right now we're pushing the neural networks to do many, many things, but maybe they're not really fundamentally capable of doing some things efficiently. Like our brain, I'm not sure if it's working like a neural network, probably not. Because if you look at brain, it's not consuming a lot of energy. It's true that it's trained over decades. Well, maybe not, maybe decades is too much. It's trained at least years, over years, but it also is very much faster at learning, in my opinion, some things. Okay, anyway, I just want to share this with you. So whenever you, for example, look at these machine learning accelerators, it's good to think they're trying to get rid of some of the inefficiency. They're trying to make things efficient, that's good. But maybe there's a much bigger efficiency that can be gained by rethinking the model of learning that we have. Okay, now I can switch to the other one. The good thing is I can also see what other people can see. Okay, so let's quickly go over some basic principles that we follow in research and also teaching. I think this is good because I'd like to set the mindset, and it may be useful for you also to think about research. I think teaching and research are actually very similar. For progress, you need to do both. We're going to cover a lot of research papers in this seminar. Some of them will be cutting edge, some of them will be maybe from 1970s, some are very fundamental. If you think about 1970s, for example, or some of the papers are also already in the teaching curriculum, right? So I think these go hand in hand. In the end, if you want to be at the cutting edge, if you want to push the cutting edge, you need to do research, but you also need to do teaching. And I strongly believe that. That's why I think having courses that incorporate both is really important. In this course, we're going to see a lot of new ideas, and I'll encourage you to think about new ideas also. Focus on what's important in a paper, fundamentally important. What kind of new insight does the paper bring into the field? It's really good to think about that. And you all can also generate new ideas, right? I think you all have the fundamentals. At least if you've taken my course, I think you all have the fundamentals really well. So you can generate new ideas based on the papers. And I would encourage you to think about that and do that. And in fact, we'll talk about that when we go into course logistics. And I think a lot of the things, everything we're doing is learning and scholarship. That's really important. Hopefully we'll have an environment here where we will freely and critically discuss ideas. And research in the end is all about openness, collaboration, hard work, and creativity, in my opinion. That's some of the principles that we follow in my group. And the quality of your work defines your impact. Hopefully you will be able to read some quality papers and maybe produce some quality research at the end, right? So people who've taken the seminar course and also other courses have done research with us and published really good papers also afterwards. Think about that at some point if you're interested in these topics. Okay, you may have seen this at some point. I'll go through this relatively quickly, but I think these are my suggestions to researchers in general. Follow your passion. If you want to do something big, there will be a lot of obstacles. You cannot just budge down if there are naysayers saying that you cannot do it for some reason. You have to follow your passion. You have to make it happen, basically. There's no other way. It's because you're doing something that no one has done, right? It's very easy for the entire world to be against you once you're doing something no one has done. You're coming up with this, I don't know, new machine learning accelerators as no one has done. And there will be people who will push back on it. Some of them will be pushing back on it so that it becomes improved. Some of them will be pushing back on it so that they kill it. That's real. And that's true in industry also. If you're a company like Airbus, for example, you'll have a lot of competitors, and some of them will be big competitors, not just Airbus. There are hundreds of companies like that today, actually, trying to do machine learning acceleration or some other acceleration, some other system design. So what makes the difference, I think, is people who really push forward and make things happen. Of course, it's not easy. You need to build infrastructure, build real systems, work hard. That's, I guess, obvious to say. And maybe more important than anything else, be resilient and focused. You have a goal, you need to make it happen, right? That's true for research, that's true for product development also, in my opinion. And I think that's how people make impact on the world. Like the systems that you've seen or other systems, they all come about because of a good mindset, goals, and focus, very focused execution, let's say. I don't think you can have that if you're distracted relatively easily. If someone critiques that, oh, you cannot do it, and then you get distracted, yes, you cannot do it. Okay, I think you get the point. You'll see a lot of papers, for example, in this seminar, and I'll try to tell you stories of the papers at the end of the presentations. In the paper, ideas may be beautiful, but making them happen in real life actually takes a lot of effort also. There's a paper process. Making it happen in a paper is difficult to begin with, but then making it happen in a paper doesn't mean that it'll be adopted in real life, right? Then there's some other process that starts to make it adopted in real life. And it's a long process. Sometimes you may have the conception of an idea in some year, and 20 years later, that idea becomes real in real life. And sometimes it never becomes real. Somebody else builds on this idea, something else becomes real, right? You never know. That's the beauty of science, I think, and research in general. Of course, seeing it real is a good thing. Usually you don't see it real exactly the way you thought about it 10 years ago, right? It gets adapted to the situation. Okay, so there are a lot of other things that we talk about, and you may have seen some of these talks and watched them actually. If you're interested, you can watch them. Okay, I'm also a big believer in open source, especially today. I think we really need to open source everything we do in science, as much as possible, of course. Sometimes you may not be able to open source some thing that you work on because it belongs to someone else, right? And that someone else is not open to open sourcing it. It happens also, right? Especially when you work with companies, that can happen sometimes. But I think in general, we open source as much as possible. And you'll see some papers that are written using some of these infrastructures. Okay, so one paper I would recommend, if you've taken computer architecture, you've already read it. Has anyone else read this paper? It's not a paper, actually. It's a transcript of a talk delivered by Richard Hamming. And people know about Richard Hamming? How many people? Okay, Hamming codes, Hamming distance. Okay, Hamming distance, I think everybody seems to know. So he is the inventor of the Hamming distance and Hamming codes and really error correcting codes in general. He really came up with error coding theory. And he was at Bell Labs. And I think sometime close to his retirement, he gave the speech at Bell Labs. And there are multiple versions of the speech. There's actually a version from 1990, early 1990, as a lecture series on YouTube that he delivered in Naval Postgraduate School, which I think is actually very nice to watch. This talk is a bit different because it's sprinkled over those lecture series. But this is the transcript of that talk, you and your research. And he talks about his opinion of how a good researcher can have impact on the world. And I'm not going to go through everything over here, and this is Richard Hamming, but you can see this, maybe we can read this. If you really want to be a first-class scientist, you need to know yourself, your weaknesses, your strengths, and your bad faults, like my egotism, so he recognizes. How can you convert a fault to an asset? How can you convert a situation where you haven't got enough manpower to move into a direction when that's exactly what you need to do? I say again, I mean, there's a lot more. There is a lot of examples that he gives actually in this talk. All of those are his examples, anecdotal. This is not science. It's not a scientific paper. I should say that. It's more of an introspective paper or talk. I say again that I have seen, as I study the history, the successful scientists change the viewpoint, and what was a defect became an asset. So what may look like a defect to you, you don't know an area, for example, I'm just picking one example, you jump into it. It may look like a defect, but it could you could turn that into your advantage, right? By thinking differently about the concepts or learning much faster in a different way, right? Okay, so he focused on important problems, for example. People should work on important problems. They should become emotionally involved, according to them. They should try and change what is difficult to some other situation, what is easily done, but still important. Basically, you need to rethink. If you're in a situation and the solution is not just commiserating, let's say, you need to think and think about how to take advantage of the situation. And there are many cases where in research as well as development, you run into these situations where you don't seem like, it doesn't seem like there's a good solution, right? The breakthroughs really happen if you actually, in my opinion, follow a lot of the things that are discussed here. Of course, it's easier said than done. You need to experience it, I think, to really understand, in my opinion. Yeah, for example, they keep saying it's a matter of luck, but maybe it's not a matter of luck. You're the one who determines your luck, right? Okay, anyway, I'd recommend this reading, let's say. Any questions? You could potentially have that as a paper in the course, but I'm not sure. I think the people who've taken this computer architecture have already reviewed that and read it, or maybe watched the video also, in addition. Okay, so if there are no questions, let's jump into some course logistics, right? So the role of this course is really go into a little bit more depth into computer architecture in a specific way. But computer architecture, you remember the slide if you've taken courses from me. It's the science and art of designing computing platforms, hardware interface system, software, and programming model to achieve a set of design goals, right? So there are many different computers. And we've seen some of them as examples, right? You may want to design a supercomputer, highest performance on Earth on workloads, XYZ. You may want to design a cell phone type of thing or tablet, longest battery life at a form factor that fits in your pocket with some cost, high point. Or you may design a general purpose processor, best average performance across all known workloads at the best performance cost ratio. Or, I mean, accelerators, right? There are many, many things that you can do with computers. But some fundamental principles are similar, and we've discussed that in digital design and computer architecture. So this course is still along those lines. We'll cover both fundamental and cutting edge research in computer architecture with a focus on papers this time. I mean, yes, if you've taken computer architecture, you also read a lot of papers. You've done some of this, but you've never really presented it to our audience. So we're going to do something different. So there are multiple components of the course. Hopefully they will improve different skills. And if you have the right mindset, hopefully you'll get a lot out of this. Clearly technical skills by reading papers or getting exposed to many papers. Ideally, I would recommend you to read any paper that's presented. Of course, that may be not so easy because I think there will be, at this point, there are 20 or so students in class and there will be 20 presentations. That means everybody reads 20 papers. Ideally, that's great, right? If you cannot read everything, well, you should clearly read your own paper very well that you're going to present. But I would recommend skimming through the papers also that are going to be presented. Okay, read the title if nothing else. There's abstract. Usually reading the abstract gives you a good idea if it's written well. Read the introduction, I would say. I think that should be enough for you to get a good idea. Again, that's not a requirement. You can get the idea during the presentation also. So, but you'll get more out of it, I think, if you read some of the paper at least. So the way I normally skim through a paper is I read the abstract for sure, title for sure, intro, if abstract convinces me that I should really read the intro. And usually I look at the conclusion as well. And then I decide whether I really want to read the full paper, right? That's kind of a good algorithm that I employ that works for me, for example. Hopefully this will enhance your critical thinking and analysis, because we're going to really critically think about all of the papers that we cover in hopefully many, many dimensions. Technical presentation. How many people have taken a presentation course before? Seminar, or have done any presentation in any course? Okay. Oh, some courses. Which courses? Just a presentation. Okay. Oh, okay. I see. Okay, in your bachelor universities, but not at ETH. Okay. How about you? Or anybody who has raised their hand? No one has raised? Okay, yeah, sorry. Okay, I see. So it's a project presentation, not a paper that was written by someone else. Okay, I see. Yeah, project presentation is also good. We're not going to do that in this course, but we're going to do some other person's papers. I guess if you've written papers, you can also recommend your papers, but to present it. Yeah, but this is going to be important in both spoken and written forms, because, well, written form, I think we'll have it at the end. You will see, we'll have a synthesis report. So hopefully you'll get familiar with key research directions that are going on by seeing a selection of the papers. Okay. So the key goal is really, what I would like you to take out of this course, hopefully, is to learn how to rigorously analyze, present, and discuss papers and ideas in computer architecture. I think we've done some of this in the prior courses, but this course is a different course. So clearly, I think we have some algorithm to achieve the key goal. The presenter, as well as the participants in the room, are active components of that key goal, let's say. So presenter definitely needs to read the paper that they're going to present, absorb it, and read more other related works. Critically analyze, think, and synthesize, prepare clear and rigorous talks, present, answer questions, and in the meeting, essentially discuss, lead the discussion, right? I think, missed some steps over here, which is interacting with your mentors. So you'll be assigned mentors based on the paper you choose. And we decide the mentors specifically based on what paper you choose, because some people are actually working on the paper. Some people may have written the paper that you chose, actually. It's possible. So interacting with your mentors is very important. And in fact, many people who've taken the course in the past said that this was very valuable for them, getting feedback from the mentors, multiple rounds of feedback from the mentors to improve the presentation, and what to talk about has been very helpful in strengthening the talk and making it better. This is what we do in scientific practice also, actually. When we write a paper, we need to present it. And before presenting it to a wider audience, like the world, you present it to, like if it's written by one of my students, for example, they present it to my group and me. And basically everybody gives feedback on how to improve and discusses what they don't understand. So with that level of feedback, things improve a lot. And the more you practice, the better in general. That's my experience. Like I remember practicing my first talk 10 times or so, first conference talk in 2003. Over time, it becomes easier, of course, but the more you practice, the better. Okay, so steps for the participants, certainly discuss, ask questions, and again, analyze and synthesize. In the meeting, you can, for example, compare things to other papers, right? You can ask questions. So usually it's good to have a discussion. And we've had very good discussions in the past incarnations of this course, even online on Zoom. Of course, in person is a bit better, I think, because it's a lot more interactive, right? Okay, and you will also have a chance to synthesize at the end of the course. You have a synthesis report where you will introspect and look back on what we have covered. Okay, so this is a very busy slide, but we'll cover a lot of different topics. We will give you a selection of papers, and you will provide us your priorities, and we will try to match to our best extent the papers that you really want to present. But I would suggest, after receiving the list of papers, I would suggest putting some thought into what you would like to present and how you would like to order the papers, because we ask you to give an ordered list of papers, not just one paper, because if you choose one paper, you may not get it right, because somebody else may choose that paper also. There are hot papers that are chosen by many people, but hopefully you'll get some paper that you like, or you think you like. You never know before reading the paper. it may be good to, well, it's good to read the titles, of course, but you can also read the abstract. Okay, so think critically. I think we've kind of talked about this, but yeah, I would hopefully this will give you some fundamentals of key first steps in research and key research directions as well. I like this picture over here. I think there's a scientific progress cycle. People read and write papers, right? So how you get inspired about a new idea, you read some paper and understand the problem, and you say, oh, I have a better idea to solve it. How does that come about? By questioning and brainstorming. And then you develop a new idea together with some other people, potentially. You collaborate, work hard, make sure, basically prove your idea and publish it. And that educates others, and that enables others to come up with other ideas, potentially, right? That's the idea. That's the virtual cycle, in my opinion. And I've seen this happen, a virtuous cycle. I've seen this happen many, many, many times, actually. And it's real, in my opinion. Even bad papers enable this. You may read a paper, it's terrible. You think it's completely the wrong approach, and you go and prove it. It's the wrong thing. Sometimes it's the wrong thing because they didn't think about the problem right. Sometimes it's the wrong thing because they did their experiment wrong, potentially, right? Or the constraints are different today, right? And that gives you a new idea. Even bad papers are actually good for scientific progress, in my opinion, from this perspective. Of course, there shouldn't be too many wrong papers, in my opinion, if science needs to be, let's say, kept clean. But that may happen too. Okay, we've talked about some of the course info. I'm going to skip this, but there are also actually two other lectures, Mohammed and Juan. Are they online? Right. There are two questions. Are they online or are they listening? I know, if Mohammed, are you online? I thought he was online in the beginning, but maybe he's not right now. Okay. Well, Mohammed is a senior researcher and lecturer, that, so is Juan. People who've taken courses probably know them. And we have, I guess, Juan, are you online? I should ask that also. I guess not. Okay. So there's also teaching assistants. These will be your mentors, actually. I don't know if I have the complete list over here. If I don't worry. You will get to see them as your mentors, of course, depending on your paper choice. And most of these folks are in my group. Actually, all of them are in my group. They're going to help you develop your presentation. Okay, I think requirements and expectations. So unlike my other courses, I would expect attendance over here. I think here it's a much smaller group, and I think attendance is required. I think you can miss some of them, of course. It's not like you have to attend everything, even if you're sick. In fact, you're sick, don't come here, please. When I'm sick, I'm not going to come here, certainly, or if you're feeling sick, right? But yeah, attendance is required. We can do online attendance also, right? And every student presents one paper. I think we already discussed this. I'm going to give you an algorithm later on. Non-presenters participate during the meeting. They ask questions, contribute thoughts and ideas. I've already said the second bullet. And non-presenters take an online short quiz after each session. 5 multiple choice questions. Usually they're easy if you follow the discussion. In general, it's easy, basically. And you'll have 1 full day to submit. And so don't worry about this quiz. It's not that hard, basically. People have done, in general, very well in this quiz. And there's an online review system. I don't know how it will work, but if you want to discuss after the presentation, you can also discuss it over there. Or you can discuss it in a more appropriate paper that comes up similarly in person as well. Right? And at the end of the semester, you write a synthesis report. And there's a sample synthesis report online. Or in one of the previous incarnations of this course, you can find it. Okay, this is the course website. How many people visited already? Okay, good. So I'm not going to tell more. You can find a lot of information there. There's Moodle. So there'll be announcements. I think Mohammed already sent some announcements. I assume people have gotten the Zoom link since they're online. So that's good. Homework 0, people are aware of it probably. That's easy. Homework, it's called homework. But it's basically, why are you taking this course? Who are you, etc. It's an easy thing. It's for us to get to know you, basically. Okay. Please make sure you submit it on time. And at some point, we'll release a list of papers from which you will give us preferences. Okay, now let me talk about how to deliver a good talk reasonably quickly. And this is actually similar to how to write a good paper review. You're really reviewing a paper, at least from this perspective, right? So I guess you should talk about what is the title of the paper, authors, and the venue, summary. Basically, give an executive summary of the paper. We're going to give you examples of it, and you can also see it from past incarnations of this course. A lot of talks are online, actually. Yeah, what is the key problem the paper is trying to solve? What are the key ideas of the paper, key insights? What are the key mechanisms? What is implementation? What are the key results and key conclusions? So this probably takes like about maybe 15 minutes or so to discuss. Ideally, you would start with a shorter summary, executive summary, like 30 minutes, 30-second summary to begin with, but you will see some example later on, not today. And then you you go into another section where you discuss the strengths of the paper. What are the strengths, most important ones? And here, start with an ordered list, basically. What is the most important thing? This paper has revolutionized computing by introducing a completely different execution model, for example. That's probably very important compared to anything else, right? The second, the writing as well. Don't order writing as well over this paper, revolutionized computing. Revolutionized computing is much more important, clearly, right? So you get the idea, I think. There's an order list over here in terms of strengths. If the only thing in the paper that's a strength is the writing is good, that's probably not a great paper, right? Hopefully not. Hopefully we won't have that sort of papers in this. But try to find strengths. Every paper has a strength. And every paper has a weakness, at least one weakness. Usually you can actually have a laundry list, but again, order the list. So this is actually where you should think critically. Every paper idea has a weakness. This doesn't mean the paper is necessarily bad, the idea is bad. Clearly, there are good ideas that have weaknesses. It means there's room for improvement and future research can accomplish this, right? And this is where you need to think even harder, because usually when people write papers, they talk about the strengths and they may not emphasize the weaknesses, right? That's unfortunately how scientific literature evolves. It's a bit not so nice, but that's how it is. It's unfortunate because I think reviewers' expectations have evolved that way. Reviewers want to see strengths, and the authors argue for strengths. So there's this vicious cycle where that happens, right? But weaknesses you need to think more critically about. Sometimes you find a strength that the author did not think about, right? Because the paper was written in 1980 and it's applied to a very different context in 2020. Systolic arrays is one example. We may choose that. In the past, we have presented the systolic arrays paper, for example. So, and then you go into more discussion mode, let's say. What are your thoughts and ideas? Can you do better? Do you have any ideas based on what you have read? And what did you learn, enjoy, dislike? What are the takeaways? And then you start discussing, as a leader, you start a discussion in the room by asking questions, right? You can ask specific questions. It's good to ask some both broad questions and maybe some detailed questions. This is actually it's very much up to you. I would suggest discussing this with your mentor. And in general, well, I will give you a breakdown in a little bit. So I think writing a paper review and delivering a talk are very similar. Whenever you're writing a paper review, you do this thing. And whenever you're delivering a talk, you do something similar. Talk, of course, is a different mode of communication. So you do a bit longer in this particular case. So this is what I would suggest in general. You talk about this part of the paper, problem, goal, key ideas, novelty, mechanism, implementation, major results, takeaways, maybe 20, 25-minute summary. It's better if it's 20. Strengths, weaknesses, alternatives, new ideas, and brainstorming, maybe 10, 15 minutes. That's what we usually target, but usually it takes longer, unfortunately. Or fortunately, people like it. But yeah, I understand. Usually we may overrun the seminar time. That's my bad news to you. So if you need to leave, that's fine. But if you like the discussion, it's good to stay. You can again look at examples from the past. Okay, be very critical. Always think about better ways of learning and solving the problem, or solving the problem or related problems. Question the problem as well. Sometimes the problem may not be very relevant anymore, right? Probably not with the papers you will see, but it's good to question the problem. This is a more general advice on paper reading in general. I mean, reading anything, I think, actually. I think, in my opinion, when I read something, even if it's, I don't know, on a newspaper, I approach it the same way, right? This person is talking about something. Is it real? What is the reason they're writing about it, right? Is it true? In fact, when you read about newspapers, you should be even more critical. Why is it there, right? What is not there also that is they're not talking about? It's always good to have this critical mind, in my opinion. Research papers are a little bit better than these general newspapers, let's say. Okay, and read background papers. I think that's actually that could be useful. If you, of course, you have limited time. I understand that, but and also mentors can recommend you some papers that can help you. That said, you can do a perfectly good job without reading any background papers. You're just focusing on your paper also. Okay, and I think in general, this is how things progress in science and engineering and anywhere, as I said earlier, how you can make big leaps by critical analysis. And we have some sample text reviews provided online and many sample reviews provided online also. Not reviews, yeah, many sample discussions provided online. You can watch the videos if you're interested. Okay, have people seen this? Okay, some people have seen it, I think. Who has seen it? Okay, people who have taken computer architecture have seen it. These are called rat holes, performance analysis, but you can apply it to paper. Basically, you can criticize any paper and get into a rat hole by focusing too much on the workloads they evaluated, metrics they used, configuration and details. These are rat holes. You may have a good discussion, and if you get into this rat hole, you may never get out of that rat hole anymore. You may be stuck in that hole, just like this rat. So I would suggest thinking about these and maybe not focusing on these too much, because you can always question the workload, right? This paper applies to machine learning, but not this other workload. Okay, make that point and move on, because that's true usually. You can always do that. Metric may not be good unless there's a big flaw over there. Again, say it and move on. There's another picture of it, as you can see, and the depth of the rat hole determines how long of a discussion it can be. Benchmark is usually like that. So this is actually from this book, The Art of Computer Systems Performance Analysis. It's a beautiful book on performance modeling. Has anyone read this or taken a class? It used to be taught. It's an old book by now. But basically, Raj Jain's book, I really like this actually. Maybe I'll read it. You can see the picture over here. This is the best picture actually. Wow, I cannot read it. It's too small here. But basically, you can think about a paper, right? The paper evaluates some performance, does some analysis. And this person says, even if the performance analysis correctly done and presented, it may not be enough to persuade your audience, the decision makers. And in this case, they're viewers also, the audience here who's listening to the paper and the person who's presenting the paper to follow your recommendations. But sometimes it's the decision maker. You're presenting this idea to someone. It may not be a scientific idea, right? You're developing something in your company and you're presenting this idea and you need to convince the boss who's the decision maker, right? And basically the list shown in this box, in the next box, I will get there, is a compilation of reasons for rejection heard at various performance analysis presentations. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new and that the analysis deserves more consideration. Also, the list is helpful in getting the competing proposals rejected. This is, of course, the funny part over here. So this is the list, basically. You can always question analysis by saying this needs more analysis. You need a better understanding of the workload. Some of these are relatively specific to the topics that are discussed in this book. Like it's going to increase the complexity and cost. That's always true of big ideas, actually. It's not simple. It requires too much state. Nobody has ever done that before. That's a fun one. Sure, that's how things progress, right? Nobody has ever done that before. I like this last one over here. Why change? It's working okay. That's true in most cases, right? Yeah, but these are things that are also sometimes a backward mindset, right? Sometimes mindset could be affecting these things. I need to be careful about that, right? Like this impacts hardware is probably the software person's mindset, right? This impacts hardware, let's not touch it. It's like it's something that has the plague, oh, not touch it, right? Yeah, that's beyond today's technology is also interesting. Okay, but yeah. Yeah, I think maybe we'll repeat this, read this also. There is no clear end of an analysis, and any analysis can be rejected simply on the grounds that the problem needs more analysis. This is the first reason. The second most common reason for rejection of an analysis and for endless debate is the workload. Since workloads are always based on the past measurements, their applicability to the current or future environment can always be questioned, which is true actually. Actually, workload is one of the 4 areas of discussion that lead to a performance presentation into an endless debate. These rat holes and their relative size in terms of time consumed are shown in this figure. And presenting this cartoon at the beginning of a presentation helps to avoid these areas. I like this advice. It's actually very wise advice. That's why I'm presenting it to you right now, so that you don't get stuck in those rat holes, let's say. In fact, when I do this in some of my courses, people actually realize that when I think I did it in many courses that I gave all over the world. And I start with this, I put this as a important principle, let's say. And sometimes the discussion, especially if it's a course where there's a lot of discussion happening, discussion goes into one of those rat holes. And somebody in the audience says, remember the rat holes, get out of this. So it's useful, actually. I've seen this in action. Okay, so there's some more advice on talks. This is actually a set of slides by Professor Kayvan Fatalian, who was my colleague at CMU. He's right now at Stanford. But he has a nice slide deck that talks about tips for giving clear talks. And I agree with almost all of the principles here, actually. For example, every sentence matters. That's true for when you write as well. The audience prefers not to think. That's always true whenever you write, actually. If someone can consume what you're saying without thinking, that's great, right? In fact, that's your goal as a communicator. Surprises are bad, meaning don't make people think. Say why before what, meaning why are you going to say that? What's the bigger reason of what is coming basically next? Explain every figure, graph, or equation. This may not be always possible, but this depends on your goal also. But I think whenever you put something that's important, you need to explain it. And when improving the talk, the audience is always right. That's a good mindset. It is true. Although sometimes you question if people are actually not paying attention, are they always right? I don't know. Sometimes it's hard because, yeah, you could argue that you should have captured their attention to begin with, right? But sometimes not everything is under your control. I guess, does anybody know who painted this painting? It's written, yeah, some people like the side channel information here. I should have. Salvador Dali, yes, okay. It's not him though. It's not a self-portrait. This is him. Maybe there's some similarity, I don't know. Not quite. Okay, this is one of his earlier paintings in 1924. Of course, Salvador Dali is not famous for this painting, right? Unless you're a specialist in Salvador Dali, you wouldn't think that this is a Salvador Dali painting. If you know about Salvador Dali, of course, right? But probably you know about this. How many people knew about this painting before? Okay. You don't have to, fine. Yeah, but this is one of his very famous paintings. You can see this is his fantastical, magical, let's say, surrealism. You can see there's a giraffe burning here. Yeah. Anyway, you can spend years interpreting this probably, but this is Salvador Dali toward the later part of his life, right? So what's the point? Anybody? Learn the basic principles first before you choose to break them consciously. That's true for talks also. Meaning, Salvador Dali became Salvador Dali because he figured out the basics of painting quickly and did this really well. And then he basically chose to violate everything he learned. I like this takeaway. I mean, it doesn't always work, of course, right? Sometimes you just choose to break things and it works. Maybe you're lucky or maybe you're really good. But it's always good to take maybe a basic principled approach. Learn the basic principles of presentation, for example, before you really choose to break them. For example, certainly you can give a talk that's completely the opposite order of what I discussed, right? And you can make it work. I'm not suggesting that this is the only way of delivering talks. But it'll be hard to pull off unless you're Salvador Dali in 1937. Does that make sense? I like this. I like thinking of things this way. But I don't say that this is the only way of actually consciously choosing to break some principles and make it really work also. Okay. So there are seminar talk examples. These are some examples. You can see this is a seminar presentation. We didn't include the discussion over here because discussion had a lot of new ideas. We chose to actually cut it over there. So it was just a talk, and it's a good talk. You can find about it. You can watch it. This is spring 2021, as you can see. This is another one, live streamed. Well, I don't know if this is live streamed. This was, after the talk we premiered it. This has the full discussion. You can see that this one lasted about an hour. Sorry. This is another one. this has a full discussion also. So these are just examples. You can find a lot more examples on last year's and the previous year's websites. So this is fall 2021, for example. Fall 2021 is last semester, actually. But we have a long set of semesters where you can find interesting examples. You may even find the paper you chose. That may happen also, because papers have been presented multiple times in the seminar, because some of them are just really interesting and people seem to choose them. We change the paper list, but we don't necessarily overhaul the paper list. You may have read the paper also prior, but up to you, basically. I mean, I'm not going to check whether it was presented before. We're just going to evaluate or discuss the paper. Yeah, you can basically find out all past course materials, and the presentations that are that people consented to make public, we made them public. Okay, how to participate? I think, how do you make the best out of this? I think come prepared, try to read and critically evaluate the paper, either before or during the presentation. Think new ideas, bring discussion points and questions, read other papers if you can. Be critical, I think that's probably the most important thing. Brainstorm, be open to new ideas, pay attention and discuss and contribute. I think that's how we can make the seminar much better for everyone, if people actually discuss and contribute. And we've had really good seminars in the past, actually. We have had very good feedback from people who attend this course. And as I said, sometimes people who come out of this course came up with new ideas, and they've done bachelor's thesis, master's thesis, or a PhD, started a PhD, and certainly published some papers based on the discussions as well as ideas that they've generated. Okay, participate online. Well, online participation is a bit hard, I think. We'll see how it goes. I would suggest, if you're interested, certainly participate, but maybe we don't have a good medium for participation. How many people are really comfortable using Moodle for participation? Okay, maybe you're better than me. Some people are okay. Yeah, how many people don't like Moodle? Okay, so this is what I expected, kind of a halfway, these strong positive and strong negative reactions. If you can participate, I would suggest participating. I think this can also enhance your experience, but I understand you may not have time also. So let me talk about guided talk preparation. So this is how you prepare a talk. We assign you a presentation date. Some people will be assigned earlier dates, unfortunately, but we will take that into account in the grading also. We'll be a little bit lax on people who present early. Study your paper and other papers if it helps to study your paper. Create a draft presentation, meet the mentor and get feedback, and repeat. So preparing a presentation takes time. Start early, as early as you can. Read carefully, critically, creatively. I think we've discussed a lot of these things. If you can try the tools, examples. I don't know, depends on the paper, of course. Consult with your mentor if there are questions. And create a draft presentation. I think we've already kind of discussed the presentation style, and you have a lot of examples. This is where you have a lot of freedom also to actually explain a concept, right, that someone else has come up with. And I think really important is meetings are mandatory, at least 1 week before the talk, but I would recommend earlier if possible. And you should really have at least 2 meetings. We plan to assign 3 mentors. I think 3 is a good number. And usually these people are people who are doing research on the topic or a close by topic, if not exactly the same topic, right? So you can learn a lot from them, actually. Usually, a lot of them have a lot of experience also. Okay, grading and feedback. Since you're not here for the grades, we're going to skip this. But okay, I'm just joking. You can hopefully you're not here for the grades only, but most of the grade will come from quality of your presentation. Yeah, we will take into account the difficulty of the paper and the time you had to prepare. And the second biggest part will come from the quality of the final synthesis paper, which should hopefully be easy at the end. Yeah, you can see the synthesis paper at the end. And then, well, it's online, as I said. Attendance and quizzes form a very small fraction. And if you participate a lot, you get a bonus also, basically. This is all bonus. And it's not, in my opinion, it's not difficult to get a really good grade in this course. And that's what we have been seeing. And people participate because they want to learn. Okay, any questions on that? Okay. Okay, feedback. I mean, we sometimes do this. We'll try to briefly discuss strengths and weaknesses of your talk in class, but we usually don't have time, frankly. If you prefer not to discuss the strengths and weaknesses of your presentation publicly, let us know. And if you prefer us to discuss it, let us know that also. Because usually we don't have time to do this. But if you really want to get feedback after the live session you delivered, you can ask us, or you can tell us, don't do that. And certainly you can arrange a meeting with your TA to get feedback after your presentation also. Expected schedule. Okay, I think this is planned. Okay, I think we have 22. I thought it was 20, but for some reason, I don't know why. Maybe this is old slide. That's possible, but expected presentation start date is 10th of March. So we should really act quickly. Now the ball is on our court, meaning we need to give you a list of papers. And paper assignment will be done online. Next meeting, we'll meet next week, I think tentatively. Maybe we'll go over a sample presentation, example presentation. We'll see. Paper assignment will be done online. Study the list of papers, check your email, and be responsive, basically. I think this may be time critical, let's say. But we'll give you enough time, I think, so that you can make an informed decision on what paper to choose, hopefully. Okay, homework 0, just a reminder, paper review preferences. Okay. Okay, I don't know. I think this is the end because I moved the synergistic activities slide to the beginning. Let me see if I have anything else over here. I don't think I have anything else. Yeah, other than I would remind you of this talk, I think. This is a synergistic activity for sure. Cerebras doesn't have a paper talking about their system. No one has written papers on this topic. They may have a white paper, which is probably not that interesting. This talk is a lot more interesting than the white paper. So we're not going to cover the Cerebras system. We may cover some papers on machine learning acceleration though. But I would recommend you to attend this. Okay, I think that's all I have. Any questions? Yes, please. Oh, what will we talk about? So we haven't decided yet, but usually what we do in this course is do an example paper review. That's what we have done in the past. But another option is potentially point you to a video that does this review. We'll see. I think I'll discuss it with Juan and Mohammed. Do you have any preference as to what to talk about? Okay. Okay. We can also talk about research. Okay, some people like that. Okay, maybe I should take a vote here. Who wants to talk about research next week? Wow, there are a lot of hands, more than I expected. Who wants to talk about an example presentation? Okay, you're kind of in the minority, but still a reasonable minority. Who wants to not have a session next week? Fine, you don't need to be, you can express your opinion basically. It's not going to change what we do in the end. Okay, any other ideas what we can potentially talk about? These are two things that come to my mind. Research, like what's going on in architecture, some cutting edge research potentially. What's going on in the industry? Okay, that's I mean, we kind of talked about that. More than that, you mean? I mean, there's certainly a lot more, yeah, we can do. But maybe if you have questions, you can ask, certainly. Yeah. Yeah, there's a lot going on in industry today, certainly, in architecture, right? And many, many companies. Yes. Yeah, so that's something that we're working on right now. The hope is that early next week, that's what we're targeting right now. That also depends on exactly how many students we have in class, because if you have fewer students than 22, then we can relax the schedule a bit, start a bit later. Not March 10th, but maybe March 17th, for example. That's what we had done in the past. Yes, please. So you will choose from a list. You'll give us a priority list. You'll say, okay, this is the paper I really want to present. If I cannot do that, this is the next paper. You'll give us an ordering, basically. Well, exactly, based on that. Well, not based on your homework, based on that ordering that you provide. Yeah. You get assigned one because we know the full picture, right? Everybody sends their choices to us and then we coordinate, we're the arbiter. If you choose the same paper as someone else chooses, well, we have to decide somehow. Make sense? Okay. Okay. I see. Yeah, sure. You can propose it. You can email us, and I'll consider it for sure. We're very flexible in that. If there's something that you really like, I'm open to that. Yes. Yeah, if you have some really hard constraint, you should really let us know. You have some saying for sure, especially for hard constraints, right? Like if you're sick during that day, yeah, we'll of course need to reschedule. But yeah, let us know if you know beforehand. Hey, these are very good questions. What else? Okay, then we're done. Hopefully I'll see you next week. Yeah. Take care. No. This is really annoying. Stop sharing. I don't understand what's going on with this. I guess there are no questions on Zoom, right?
No, but someone says it costs 60K per week to rent the Cerebral system, I guess.
60K per week.
60K per week.
Okay, wow, that's a lot. Okay, bye.